All right, everyone, welcome to another episode of the TWiML AI podcast. I am your host, Sam Charrington, and today I'm joined by Roland Memisevic. Roland is a senior director at Qualcomm AI Research. Before we get into today's conversation, be sure to take a moment to head over to Apple Podcasts, Spotify, or your listening platform of choice. And if you enjoy the show, please subscribe, rate, and review. Roland, welcome back to the podcast. This is 3 for you, right?
Yeah, thanks. Great to be here. And I think it's the third time. Yeah, it's great to be here again.
I'm really looking forward to digging into our conversation. We're going to be talking about LLMs and reasoning and how your work over the years, since that initial conversation, has evolved to really take on these topics. Since it's been a while since we've spoken, and the first time since you've joined Qualcomm AI Research, I'd love to have you kind of talk through your background and how you got from 20 billion neurons to where you are today.
So last time we spoke, I think it was around 3 years ago, something like that.
And the first time
Um,
about 5, I think.
yeah, something like that. And we talked about the company that I co-founded, and that was 20 billion neurons. The things we've been doing there, which essentially has been the stuff we've been doing before and then during the company and are still doing now at Qualcomm. We all joined Qualcomm as part of an acquisition around 2 years ago, so not too long after last time we spoke. And we are now with the team over here and pursuing essentially the same research direction around combining perception and language so that you can build agents that can drive an end-to-end vision for AI further than we believe other approaches to AI have been able to do that. And so that has been a very long story over the years. I was actually already interested in this particular kind of thing, like building a situated agent rather than modules that solve certain subproblems. Previously, when I was on faculty at University of Montreal, and then I realized it would be best to pursue this at a company, compute resources, data, all of these things, and and now we moved all over to Qualcomm and continuing along the same lines.
Awesome. Yeah, I remember what led to our first interview was I think I ran into you and a couple of your colleagues at, I think it was like a rework conference in Montreal, and you were demoing um, this data set that you'd created that was, trying to capture, actions. Like, I think the way you described it at the time, which I thought was really interesting, was, all of this work we've been doing in computer vision was noun centric, and you were trying to do verb centric data sets. And so, how did that work lead you to, what came later with the Fitness Ally project and your interest in reasoning?
So you are talking about nouns and verbs, which already kind of alludes to the whole reason for all of this, which is essentially language. There has been a really long-standing tradition, I guess, over the last 50 years, probably 50 plus years. Um, a tradition, or let's say assumption, that language is a key ingredient to any kind of human-like intelligence. And there have been many efforts, right, with Eliza and all of that stuff over the decades. And I'm definitely a deep believer in language as being a must-have ingredient to build intelligent systems and to make them human-like in some way, so that it's a key ingredient to human-like AI. And interestingly, the community at large, I would say, discovered around 2012 after the ImageNet incident happened and people were training networks on ImageNet, which worked, okay, which is cool, and it kind of revolutionized vision in many ways and so on. But more importantly, that the features, penultimate layer features or whatever, that the model learns in response to being trained on those 1,000 classes are highly universal visual features that can solve many other vision problems besides categorizing cats and dogs and houses and cars and such things. Um, so that was from a blunt language perspective. It's true. It was sort of about nouns, not about verbs. But I think it missed a more fundamental point um, that is behind all of this, which is the moment you think about labels not in terms of one of thousand, like you say label 37, but you actually give them names like fish, but then later you do that for verbs as well, and maybe for adjectives and adverbs and etc. etc. So once you have a rich representation of the kind of concepts you want the model to acquire, then you have a much more fertile ground for the model to develop features that are then useful for downstream tasks, right? And so the name of the game has been also at the company, how can we drive this end-to-end vision where you train a network supervised on one task, a bunch of tasks, however you want to call that, on something, you train it supervised, not to solve the task, but in order to instill features in the network representations that are going to make it in some way universally intelligent. And so I think it's once you want to do that, you want to instill capabilities in the model, you wind up using language. There's no other way than using language to represent the concepts that you want to have as a supervision signal to the network, right? So in that data set that we discussed some 5 years ago or something in one of the earlier discussions that we had was called something something, and it was about adding verbs, but also adding adjectives, adverbs, etc., etc., etc. In other words, adding captions to videos and training a network to make predictions, so predict those captions, detailed predictions, like there's an object that fell down over here and it hit the other object, or whatever, crazy, weird prediction stuff. Again, not so that the network is able to do this kind of weird stuff, but so that the network learns about things like occlusion, temporal persistence of objects. It learns about objects in the first place, right? When an object moves, it doesn't usually teleport itself, and just the idea of object comes about partly because there is something persistent about it across time, even though you have motion and these kind of things. You can learn about material structure, it knows something about rigidity, and so on and so forth. And so it's a way to instill cognitive skills, like base skills, perceptual skills in that case, in the model, hoping that it would make the model smarter. That whole vision then got pushed further and further, case to cases where the system was supposed to be chatting with the user in real time, sharing a joint space. So you're like in front of a table with some objects on it, or the user is doing things or something like that. And so you have a face-to-face conversation just like we have right now, and you can show things and discuss things and basically immerse the model in a real-time, real-world environment so that it learns common sense capabilities. So it's common sense that language can easily be used. Maybe some people would say misused, but maybe that's one of the main reasons why language is so successful in evolution, can be used to instill in models, right? So having a shared name for things. We call things fish, and the one individuum doesn't call it label 37 and the other one calls it label 501 or something like that, but there is a joint notion and we both call it fish, and so that way we can teach each other about what the objects are, and we have learning signal in human societies and whatnot. And the same thing carries over, I deeply believe, to AI systems, where once we use language, we can align the representations with the ones that we have fairly well, and that way get some kind of common sense and human-like AI going. Yeah.
And how did this lead you to Fitness Ally, which was ultimately the product that you were building at 20 billion neurons
It
and
was one.
continues today as a kind of a platform for
Mhm,
research?
mhm. It's a bit broader than that. It was one product. It was one
Okay.
uh, instantiation of getting value out of this weird system that we were
Yeah.
basically up to, right? So the idea being, okay, we want to build end-to-end systems. We want to drive this end-to-end learning to the end. The system should be able to have auditory input, visual input. We didn't go as far as sensory input and robotics because we felt like we don't want to deal with mechanics and whatnot, and didn't feel robotics is quite up for it. So, but it's all kinds of sensory and typical human-like sensory input, and specifically vision and audio. And it has to have a body, so it has to be able to convey things by moving around and so on. And it has to give you auditory output, speaking to you, and also visual output in the sense that there's a camera looking at that creature that we built, so that it can basically have a sense of a conversation with you. So this is end-to-end learning pushed all the way to the end, save for robotic, like true embodiment. So sometimes we call this virtual embodiment. So we wanted to build a virtually embodied AI system, a virtual robot, and exposing it in real world conversations with real people in real time so that it learns something about the world that it would just never learn otherwise if we train it end to end, supervised on ImageNet style labels and these and or action labels for videos, etc., etc. So that was the vision, and we were convinced that this is the only way to build human-like AI systems, train them end-to-end on the right setup of tasks, and those tasks have to be of this nature: sensory input, language, back and forth, and learning that way. Um, and so we tried a whole bunch of stuff to turn this into a vision that is also commercially viable. And so we built things like retail assistants that would teach you things about objects at an end of aisle display. And then they tell you, do you want to try this on? Maybe sunglasses. There was one demo that we showcased at Nerves at some point. And then we had various other use cases where this avatar would just provide value. And then fitness was one of those explorations that we did that stuck very well. And this is probably not surprising. Fitness is a case where you can have real value if you have a companion of sorts that knows you or through the days, weeks, months, years, knows how you've been performing your exercises and so on, and then guides you by giving you feedback and so on. There's an obvious superficial utility in that that system can tell you what to do to avoid injury, maybe, or to be more efficient. There's a much more subtle and much more powerful one, which we were also after, which is companionship. So that system, by knowing you and knowing how you've performed your push-ups in the past and how many you will be able to do, is much better at holding you accountable than some bean counting app that basically just has a dial that goes up, increase a number that increases every time you do one push up or something. But you feel a little bit more, you don't want to disappoint that trainer in front of you that remembers yesterday you managed to do this many, and today, come on, you're going to do maybe one more, and so on and so forth. So some degree of companionship, and so that got stuck and worked very, very well, and users liked it, and so we pushed really hard to push that further. It took a while to land on this particular type of use case and vision as a use case that straddles between these two, which is crazy, right? If you think about it from a business point of view, maybe from a research point of view, it's a system that is really useful and provides real value, and at the same time, it's intimately linked to this end-to-end vision of having an AI system that has to have a real-time language-driven conversation with you about stuff that's happening in front of the camera, which I still believe is the only way to build systems that are human-like, sufficiently human-like. And so now Fitness Ally is a system that we had in the app stores, various app stores, and people were subscribing and using. And now after the acquisition, we're still pushing this further as a demo. And for example, combining the language capabilities of typical LLMs pre-trained with the visual capabilities, also trained in part through language of that perception stream that comes in. And it's still one end-to-end system that has to learn and be fine-tuned end-to-end in order to do what it's doing.
I was going to mention that a lot of this research predated LLMs. How have LLMs kind of impacted Fitness Ally, but really more broadly your research interests and research agenda?
Yeah, it's interesting. So we had maybe so we did deal with predecessors of LLMs, which used to be LSTM based RNNs, right? So RNNs had to be a part of this whole stack because you want to have language in order to instill capabilities and so on. So you need to have an agent also that uses language in order to do stuff. We had early experiments of various nature where we, for example, showed that if you train a model that has an RNN-based language decoder, autoregressive language decoder, linked to the visual input, and you train it across captions. So, like for example, in the something scenario of increasing complexity. So instead of doing classification, you do various levels of increasingly sophisticated, detailed description of what's going on in the scene. that then you learn better features for downstream tasks that are better generalizing and that are better infused with a degree of common sense understanding of what's going on in the world, right? So we had these kind of studies. They used to be RNN based. The big difference, the big transition, which I think is going to be a transitory transition, by the way, historically in AI. But the current transition to attention and the lack of true recurrence has some benefits in training, and so they are much better at instilling language capabilities that are so deprived of, on the other hand, deprived of visual input, perceptual input, but they are better at just handling language and so on. So that's much better right now. And so it's easy, though, since those models are also autoregressive. So they are recurrent in quotes. They generate one token at a time, and they can still be agentic because of that. So they can still have a back and forth conversations and leverage all of those aspects of language. But the good thing about that way of getting at language is the current way of getting at language is that you can train them in parallel on parallel hardware, which you cannot as easily do with RNNs, right? When you have an RNN that generates one token at a time, you generate a linear sequence of events that you're going to have to backpropagate through. So you have a factor t, where t is the length of the sentence or whatever output that you generate, as a multiplier in the computational complexity, time complexity of training. There's just no way around it. You're going to have the t. You're going to have to generate one token at a time for a certain amount of time until you have your attempt to, say, replicate a training case or something. When you look at a transformer, that disappears because now you can just have an input. Every column that processes the inputs can just try to predict the next token. You get losses across, and you can just do one in one step, so to speak. You can process this whole sequence, and so this factor t magically disappears as a constant that influences the training complexity, time complexity, and so you can train them much faster. So I think a reasonable assumption is that if you would take an LSTM based old school LLM, whatever, small SLLM, small large language model. Uh, it has to be large, so and you would train it for like 100 years, then we would probably get something as good as, or probably even better than, a top shelf GPT pre-trained language model. It's just you would have to wait 100 years to train it, and so that's why it's currently the field is dominant. Any language stuff is and AI at large is dominated by parallel stuff, right? But it's a coincidental technical.
I think the point, just to kind of linger on that last point you made, I think you're saying that, um, the LSTMs, RNNs are not fundamentally inferior in their ability to capture language, but rather from a practical perspective of training them, they are not as efficient by a significant degree than transformers.
Exactly, and that
In spite
somewhat.
of like the difference in, transformers have this ability to capture longer context. Are you saying that if you can make t arbitrarily long and you had sufficient compute to train with an arbitrarily large t, is that part of what you're saying?
It's part of it. So you can add other things to that, right? I think
Hmm.
that complexity is a key factor.
Yeah.
There are benefits, obviously, and it's the verdict is out. Nobody knows, right? Like, what if you had recurrence, yet you have the ability for some long range stuff by some essentially what humans are doing with some kind of reverberating short-term memory, right? So things that you just said, there's an auditory loop. You remember that for a short amount of time, but it's quite accessible to you at any moment. So the last few seconds, you still have them somewhere reverberating around, and so that the ability to just grab that and take it and use it and stuff is probably another aspect in which GPT whatnot is superior over some LSTM, but there wasn't LSTM or RNN or something like that. Or even back then, people were exploring many, many different incarnations of RNNs with many different like clockwork type models where you look back a certain amount of time. And then RNNs were the initial type of architecture where even attention in an encoder, first in an encoder decoder kind of scenario got explored. And so it's very natural to have these uh, uh, to deviate from these linear, state by state transitions or something like that, even in an RNN. By the way, interesting. I think it's probably a bit of a trend also right now with papers that are pointing this out. But there's an interesting fallacy for taking that shortcut, like pretending to be recurrent, but actually being fully parallel and momentary, like a GPT style model is. And that is the fact that they can be pseudo recurrent in the sense that they can generate sequences and seem to rely on past actions to do current actions and this kind of stuff, where in reality they can also fall prey to being tempted by pattern matching, essentially, right? So they can basically find similar patterns, or they can be doing certain actions just because the context up to now just has a certain signature that makes it look similar to certain training cases, after which that action is also the right action to take or the model learned to take. And so some of the capabilities that seem very striking can maybe be explained away by a certain degree of pattern matching and then something much simpler. And one problem in which this is actually turning into a real problem is length generalization. So there are various studies lately popping up that study what happens when you take an LLM, train it on a certain length sequence of a trivial task like multiplying things in parity and whatever, like certain symbolic tasks, and then you try to have it generalize across beyond that window that it was trained on. And so I'm not talking about context window, right? The context window might be much larger than any of those either training or test situations, but it is just they were trained to solve instances of a certain tiny lengths and then try to generalize into a slightly larger length, and it completely falls apart because it doesn't understand the gist of the problem. And that, where does that come from? Well, it comes from the fact that the model isn't actually recurrent, so it doesn't have the same notion that you have about in order to solve this multiplicative whatnot problem, I'm going to have to take this token here, then I have to combine it with that one here, and then I have to do this. So this whole sequential nature of arriving at the answer is not there when the model learns this on the training data, because it gets tempted to just do subgraph matching on instances that look similar to training data, and then it just comes up with the answer. And so it seems to being serial in sequential in processing those multiplicative problems, but in reality it's not. And that is a big problem that is actually probably going to require recurrence to come back. But now people can approach it from a different angle. You can start with a model like that and then sprinkle in recurrent connections and fine tune them and see what happens. But I think recurrence will be back, right? It's not. It's. I have no doubt.
I was going to ask, when you say that you think LLMs are a bit of a transient state. It sounds like the next state, or n plus n, n plus one state is some degree of recurrence coming back into the model. Is that kind of what you're thinking?
Oh yeah, yeah, exactly. That's at least one way in which those models are going to have to evolve, and
Yeah.
will evolve, and it's okay, right? So they provided a
Yeah.
lot of value, a lot of insight.
Now, I want to shift gears a little bit and jump into this idea of reasoning, particularly in the context of language. It's been a topic that I've been super interested in, as have many of us in this field. And one kind of snip or a soundbite that I've kind of come to is that LLMs do not reason or cannot reason, but they can produce, uh, results that are, seem like reasoning. And the idea is to reinforce that, they're next token generators. They're not following a process that we might think of as reasoning, but somehow the result of, running this next token generation, some number of times looks like or produces the results of reasoning. And I just wanted to throw that out there for you to,
I don't
pick
agree with that.
apart. You don't agree with that? Yeah, let's get into it. Tell me why.
Tell me a human being that is not producing one micro action at a time, one after the other, right? It's not possible. So at the end of the day, atomically, whatever you want to call this, the robot that we are, the robots that we are, whatever, or when we talk, right, the language that we output, it's always a string of, let's call it tokens. Well, you might call it whatever you want. You can also say
Mhm.
phonemes, whatever. We could have done it on the audio level, even if we had more compute and stuff, or whatever. Let's call everything tokens that a model outputs, that an agent outputs. You never do anything but generating one token at a time. That's just a fact, right? There is space and time, right? The constraints of our physical world, and time just advances, and we can just do one thing at a time, and that's just what it is. It's just a fact of nature. And so if we
I
build an
don't know
AI
that I
system.
necessarily agree with that. What we know is that, because we've got, one vocal apparatus,
Mhm,
like the output is serial from a words
mhm,
perspective,
mhm,
of course. But from a biochemical perspective, there's lots of things happening, you know, at the same time. They're just serialized by this, output device. And I guess, um,
mhm. That's absolutely fair. I agree with that, and I agree with partly with the idea that some of the chains of thought that you see are pretend reasoning, and the lack of recurrence is just one example of that. That's for sure.
mhm,
So if you, on the other hand, want to build an intelligent system, I think we have no other that is human-like. So if we really want to advance this agenda, like building more human-like intelligent system, so we have no other choice than building an agent that has a perceptual input and has one output at a time
mhm,
actuator, and it goes through. It is an autoregressive model. At the end of the day, it has to generate one thing at a time, influenced by whatever it sees right now and the history of whatever it saw before and whatever it has generated before. So that's it, right? That's the universal definition of an agent, whatever reinforcement learning agent. And
mhm,
there's a lot of benefits to formulating a system like that versus going for feed forward networks and solving like vision and then solving this and then solving this. The benefit is that the driving force in neural nets in general, starting with ImageNet pre-trained networks or speech and whatnot, is it's end-to-end learning. So you can do supervised learning and you get domain transfer, right? So that benefit is real, and that's what I believe is the 99% of what drives AI forward. That benefit can carry over to agentic situations where you want to build an agent just as well if you take as the artifact that you're building an agent that has to do one thing. And this is a real agent. It's embedded in a real world that has time marching on, and it has to do one thing at a time. And the environment is unforgiving, and sometimes it has to do things fast in order to catch up, whatnot. But it is an agent at the end of the day. When we train agents like that, and so when we define the AI model not as a function but as a procedure, right, as an agent that does things over time, then transfer learning, I believe, can play out in the realm of action sequences and decisions and all of this kind of stuff. And that, I think, was a big problem with a lot of reinforcement learning in the past. So in lots of value-based approaches and the whole RL history over many years, decades actually, the engineer was in the driver's seat, and you have a value function, and you design the system based on a time slice that captures the history and the assumptions about the future and so on, and then you use that in order to define an agent yourself. What this is transitioning to now is a situation where the system is a neural net, and you leave that damn neural net alone and just define it as an agent, and then expose it to various tasks that are agentic in nature, so that are sequential, where you have to do this and then this and then this and so on and so forth, so that the cognitive skills in referring back to things you have done before, in understanding words like first, second, third, and so on and so forth, understanding that there are actions you can choose from and so on, that this emerges in response to the task you train it on. And so now transfer learning can play out. And that's this domain, and the domain of making a better agent. So from that point of view, I think there's just nothing other than an autoregressive model that will lead us to better AI, because you're just missing out on the agent aspect, right? And humans are agents, and our language is deeply informed by um, humans being agentic. We know about past and future and first, second, third, and this and then that, and so on and so forth. So I think it's even, you could claim it's hard to find a significant number of words in the English or in other languages that are not in some way infused with semantics that has to do with the agenticness of that human that uses those words, right? None of those words are represented in the same way in a GPT pre-trained language model yet fully, because they are not trained in agentic scenarios fully yet, etc., etc. But since it's an autoregressive model, it has the potential to absorb this meaning that goes beyond what it sucks up from Wikipedia and web language and so on. And so that's what's exciting about this.
So, when you think about kind of crafting a research program to explore these kinds of issues, to understand what reasoning means, because that's one of your main focuses at Qualcomm, on the research team there. Like, talk about how that plays out. Some of the individual works that you're exploring to kind of get at these questions around what is reasoning and how do you create. Uh, uh, reasoning capable agent systems, agentic systems, with these building blocks that we're left with, LLMs, recurrence, whatever, these autoregressive models.
So first of all, I think it's reasonable to proclaim that reasoning exists because of language. That's one distinguishing factor that distinguishes human intelligence from other animals to a large part. Not everybody would agree with that, but I think language has to play a key role in that. And so when we talk about reasoning, we foremost talk about language. And that incidentally is also the way in which reasoning has made a huge advance in the last few months, actually. It's because language has entered the realm, right? So it's like,
Right.
arguably, it's been language had something to do with it. Um,
Yeah.
there is the long-standing theory in psychology and in cognitive science of dual process type scenario or architecture, whatever, that the human brain adopts, which is there's a system one and a system two. Dan Kahneman, Nobel laureate, has been a very, very outspoken proponent of that view. Has written a very famous book, Thinking Fast and Slow, about this and so on. And so that viewpoint says that there is a fairly clearly, a somewhat clearly distinct set of cognitive capabilities, which can be called system one and system two, where system two is the stuff that is serial and slow and deliberate, very human-like actually because of that. And then there's the system one stuff, which is fast, reactive, often pattern recognition, often very perceptual, like recognizing in a matter of milliseconds, recognizing as a predator, whatever it is, and that there is this interplay between these kind of. It's not definitely not modules. That's the way in which this can mislead a lot of people, but it's sets of. They say clusters of capabilities that humans have. It's that interplay between the system two and system one that is both fascinating and that probably holds the key, at least many believe, to really advancing AI and making it more human-like and so on. And so system two, to many, and as so to go back to that original point, is somehow intimately linked to language capabilities. And when we study language, then we are automatically drawn to problems to do with solving long range serial abstract type problems that only humans can solve. And so that has made a lot of inroads recently because language models, just normal pre-trained language models, work very well in tasks that involve mathematical reasoning, abstract reasoning of various sorts, and so on. What's interesting to note is that a lot of that reasoning capability is, well, first of all, it's interesting to see that it comes kind of for free, right? So surprising to everybody. It's once you master language really, really well, you're really, really good at doing various kind of mathematical reasoning problems and so on. But it's also interesting to note that a lot of stuff is still missing in these kind of systems. So one playground that is popular now is code generation and code execution, and mostly code generation, right? The models are asked to generate Python programs that do various things and so on. But it's interesting to note that they arguably fundamentally must be missing some conceptual aspects of the code that they write that completely deprives them of getting creative and good programmers at the end of the day. And I think a lot is still needed to sort this out. So here's a very simple example. When you are aspiring early computer programmer and you learn about variables and this kind of stuff, you adopt various kind of metaphors about what the heck you're doing in your code. Like, for example, one of the metaphors you adopt is variables are containers. They're like boxes that you can put stuff into. So you can say a equals 2, and then the container a holds the value 2, and you can also put, say, a equals 3, and then it holds another value, and so on. And you learn various things that are building upon this metaphor. Like, for example, if you want to swap the values into variables, like you want to set a to what b was and b to what a was, you cannot trivially do this, except Python has some shortcuts for that. But normally, what you have to do is introduce a third variable c, and then set c to a, and then set a to b, and then set b to c. So you need to basically take this thing, move it here, so you can exchange these two values, which is something you also have to do in space if you want to move two objects around and exchange their position. Right, one has to move out of the way, the other one can go there, and this kind of stuff. So there's some very deep common sense grounding in this stupid simple concept that I'm just bringing up randomly here of swapping the values of two variables. Now, arguably, if you look at a GPT pre-trained language model that is good at code generation, it's lacking, I would at least argue, some of that metaphorical underpinning, that idea of a bucket, or the idea of some spatial rearrangement of sorts, and these kind of things. And it doesn't hurt in a lot of these test problems and so on, because it can be a pretty dead metaphor. You just know that here you have to switch variables, because in this type of algorithm, that's what you do in this point and this kind of stuff. But when you then want to build larger systems that rely on similar ideas, where you want to shovel things around and this kind of stuff, my assumption at least is that you're just never going to get there unless the system actually has some kind of imagination of what's going on as it is doing these kind of operations. And so that is actually a very, very difficult and long range problem. How do you instill these metaphoric analogy type pieces of knowledge in a model that is supposed to generate code and this kind of stuff? And so one path to it, I believe it's the only path, is to link this language model with visual or other perceptual input. Visual is just very convenient. That's why we've all been on visual input for many, many years. So that the stuff that it is talking about and reasoning about is actually grounded in some kind of environment, or some kind of reality, right? It's similar to, if it's an agent, it can learn about procedure. It can learn what the word first means. If it's an agent that is dealing with spatial configurations, say, of objects, just to begin with, it can learn about why swapping of variables requires another area that you can move something temporarily to. Don't get me wrong, you could ask an LLM to explain the whole bucket aspect of variables, and it would do a very good job at explaining it to you. But that doesn't mean that it would actually understand the notion of some spatial proximity and whatever you have in your head as you're solving these kind of problems.
But do you
Arguably.
think we can get there with a visual grounding approach?
I think we will get there with visual and agent type grounding approach, right? So
Mhm.
if it's an agent that has to do things actively in some kind of environment, I think we can get a lot of additional signal that informs the embeddings. So when people say grounding, they often think of like when the language model says dog, it doesn't have a visual understanding of what it's talking about. So it says dog, but it has no clue what it means. And then that word gets informed about what a dog looks like if we have language models that can also do vision and this kind of stuff. But this only goes so far. I think grounding goes significantly further than that. And so some of the things that we are studying in that realm are things like visual reasoning problems where you use language in order um, to solve them. So you have arrangements of objects, say in a scene. There are many data sets. Something incidentally had a similar flavor back then, the data set that we discussed before. Um, it's a difficult, finicky task where you have to pay a lot of attention to what's going on. You have to sometimes track objects. You have to sometimes know that an object is hidden, is still there, even though it's hidden somewhere. And if it's maybe moving, there's some kind of inertia, it's likely to continue, and so on and so forth. So you have to do various finicky things, but they all have to be linked to language. And then you ask questions about what would happen in the scene if this object wasn't there, for example. And then you have to say, well, then it would continue and hit this other object, or whatever the domain problem is. And so that's one of the things that we're studying.
Sounds like what you're describing is the Look, Remember, and Reason paper, or the setting for that paper.
That's right, though it spills over into many other problems. But these are all very related. That's everything is about grounding and understanding what language, the role language can play in building systems that are smart. Yeah, but that's right. This the scenario I just talked about was like very seriously and fundamentally studied in that paper, LRR.
So how is the like what's the setting? How is that problem modeled in that paper?
So in that paper, we are using a frozen language model to have the ability to have chains of thought at period. Um, then we have an adapter that can take a visual input coming from a off-the-shelf, run-of-the-mill vision model, possibly also pre-trained, to project onto the embeddings of that language model, so that those embeddings specifically they can go across layers, but specifically in higher layers can have some information about something that is visual and that is outside of the model itself, and so on. So when the model says things like left or right or so on and so forth, it's going to have a sense of what that means in this environment that it's training in. So it's basically architecturally super simple, and I'm actually a very big fan of very, very simple architectures. I don't think AI will be solved through architectures, but through smart ways of using data and so on. So it's a very simple architecture, nothing special about it. Take a language model, take a vision model, adapt them, let them be connected. But with some constraints that have to be present. So you have to be careful in setting this up. For example, the model has to be able to attend to the visual input in a top-down fashion. That means that if you ask a question about, say, the video that it's going to watch, and then let it watch the video, then that model needs to be able to pay close attention to what's going on in the video as a function of the question that you posted, right? So in many cases, when you talk about vision language models and so on, it's like there's no such top-down effect that takes place where the very perceptual processing, visual processing in that case of the input, has to be modulated by what you're planning to do with the visual input. So if you're counting events, then you have to pay attention to one thing. If you are counting objects, to another thing. And if you're saying what would happen if, then it's to a third thing. So there has to be top-down influences between this, so it cannot go just one way. So the embeddings have to be influenced by the visual input, but they also have to be able to determine how you're going to process that visual input. And so a bunch of these things have to be carefully designed so that that very simple system at the end of the day then is able to misuse, if you want to call it that, or use its pre-trained language ability to do reasoning in those visual inference scenarios. And so a specific aspect there that we explored in that paper is to let the model generate rationales. There is a concept called chain of thought prompting in abstract reasoning, where people discovered it's much better to let the model describe in great detail the chain of thought leading to a solution rather than letting it output the solution. So we can do the equivalent thing now in this visual domain where the model can uh, be asked to um, infer certain aspects about that, say, video that we believe is going to be useful down the road to be able to solve this particular task. So we're able to instill cognitive capabilities by phrasing them as language that we think are constituents in solving difficult reasoning problems, like tell me what would happen if this thing was over there, etc., etc. And so it goes back to the all the way, right? It's about using language as some kind of tool so we can broaden the conceptual richness that the model is exposed to, and then just use supervised learning on a surrogate task, essentially, on some kind of auxiliary task. So we instill the skills that you need to solve a problem. But what's different to 2013 is it's agentic to some degree. It's video. It's processing in real time, and it solves very hard problems, arguably hard problems, although they are mostly synthetic type problems that are studied in this kind of community and this kind of domain.
And then in the context of that paper, how do you benchmark the work?
Yeah, it's usual. There's accuracy measures of various types of various tasks, and the usual. Right? You go if 92% versus 95%, and we do very very well on a lot of those tasks, despite having this very very simple architecture, which is basically what
Are
it
you
is.
benchmarking? Like, is it you? It sounds like you're using common benchmarks. Are they
Mhm.
benchmarks that specifically try to get at examples that
Oh yeah,
confound non-visually trained models, or
I would.
is the idea that this visual grounding by using conventional benchmarks, this visual grounding, if it produces an uplift on the conventional benchmark, it kind of validates the assumption that the visual grounding is generally useful.
They're essentially impossible to solve without combining vision and some kind of reasoning machinery over the
Okay.
visual input, right? What's different now, I think, but this is in which way this is aligned with current trends as well, is that it's end to end. So we are trying to just train a system end to end to be able to do these kind of things rather than building a system on a design board from components and figuring out you need to do object detection. Once you know where the objects are, you need to do this and this. It's like, no, it's none of that, right? There's an end-to-end neural net, just gets pixels, and then there's a language model that can answer questions about and have a conversation essentially about what's going on in the video stream. They are probing various reasoning capabilities. So one of the benchmarks that we're studying there is called ACA, which is actually a task derived from a task that is administered to children sometimes to check various cognitive capabilities at various ages. And that tests things like causality and confounding factors when you draw inferences about properties of objects and this kind of stuff. And some others are much simpler. For example, there's one which is something that incidentally we also studied in a real world scenario before, which is essentially the shell game. So you have a bunch of cups, let's say, in transparent cups. There is a marble below one of them, and then you move them around, and you have to in the end say where did the marble go, under which cup is the marble. That benchmark that has this set up in a synthetic way is called CATER, CATER, and what it comes down to on the AI, like cognitive capabilities level, is you have to be able to do tracking anonymously, because in that particular task it's even harder. It's like you have to first of all, you need to remember where that marble is. You need to make sure that you follow the one of the multiple cups that has it, or in this case it's some kind of cylinders and stuff. Then the cylinders can be occluded by other objects, and then the whole thing can move around. And so you have to basically make sure you pay attention to what's going on in the scene and know about object permanence implicitly and these sort of things to be able to answer it. And that end-to-end model also does very well on that. I mentioned we studied this before. This was actually some exploration that we did in the company at 20BN a long time ago, where you would do this shell game thing. So playing with this marble under the cups with an avatar that is looking at you as one of the the things that the avatar is supposed to do, right? So it's supposed to play this game with you, and then you are the one who moves around those objects, and then the avatar has to prove what it can do by basically saying, okay, I think the marble is over here. These kind of things. Yeah, so those problems go beyond the types of abilities that classification tasks and so on, captioning tasks in many cases get at. They get more at long range capabilities, having a certain degree of memory of what happened before what, and these kind of things. And that way, they get much, much better at questions around common sense. So, those problems beyond abstract reasoning that you have in math word problems, and so on, are much more closely linked to what humans typically call common sense, and that is those things like object permanence and gravity. There's gravity. If I let loose, then it's going to fall that way and not that way. And so there's this amazingly rich and vast set of properties and facts about the world that you have carry along with yourself that helps you in many scenarios be really, really good at solving these kind of problems. And AI systems just don't have it. And once language and perception grow together appropriately, that ability will be there. And that is a big step up for AI.
So another recent paper that you worked on is in the domain of situated chat. This was a paper at the CVPR Embodied AI workshop. Can you talk a little bit about that one and what it's trying to do?
That paper is essentially a logical continuation of the work that we did at 20BN towards the fitness coaching AI system. And what's different in this system is that we are now using large language models rather than LSTMs and whatnot to that are pre-trained also to phrase what kind of improvements you can make, how what you're doing relates to how you've been doing in the past, and so on. So now it's much less rigid and much more open-ended and much better simply at generating language. And another change is that in the past, we were always on this mission that we want to have an end-to-end system where everything is happening end to end. But at that time, text to speech, for example, wasn't quite there yet, and we knew at some point text to speech will just be there because neural nets are advancing fast and so on. But until then, we're just going to have to use whatever we can in order to let that avatar say things. And so in that case, we actually wrote lines and had them acted out and so on for that avatar so that it can say certain things to the user in the right moment. What's going on in this new work now is that the language model decides on the phrasing of certain things that it wants to tell to the user. And a 2023 text to speech model is used to turn that into audio to actually emit that speech back to the user. And so that makes the whole development cycle much, much easier for us and faster. And it makes the whole system behave much more natural than before. There is still a ways to go, by the way. So right now, there's still a state machine, unfortunately, in the model, in the whole system, that decides based upon the visual input what has to happen when, and then what type of things have to be said to the user in what kind of scenario. Now we are working towards making that end to end by syncing that back into the language model so that the language model becomes the system that is really in the driver's seat and decides everything and behaves the way it should be. So it's not just the communication part, but it's also the thinking part in this whole system.
You've also got a paper that explores the way that drawing on a canvas type of environment can act as grounding signal for LLMs. How does that fit into? Um, how does that complement the previous couple of papers that we talked about?
So, well, there hasn't been a lot of buzz lately around image generation, thanks to uh, stuff that got kicked off with diffusion models, previously DALI 1 and so on. Um, so here we're taking a completely different route towards generating images in a very, very constrained, simple scenario. It's not so much at the moment about generating beautiful images, but studying um, how we can generate images by having an AI model that is agentic again, right? So we want to have an end-to-end system that is autoregressive and hence it is an agent and that can take action on a pen if you want, or maybe some other types of drawing utensils, and then use those and learn to use those in order to create some kind of imagery. In this case, it's drawing, so we're just studying this in the context of line drawings, and the model has the ability to draw lines and do this for long enough until the object is appearing that you want to appear. The model, incidentally, is very similar, almost identical to the look, remember, reason, a simple model where a pre-trained language model has an adapter that allows it to ingest visual information, and there can be this back and forth between the visual information and the language capability. So it's architecturally the same, also by design, because again, I don't think we need to develop a fancy architecture, but rather use the right overall framework and then fill it with live through training data. What's interesting about this, though, is that as the model draws, since it has visual input, it can learn to make use of what it sees in the moment, right? So the model, it doesn't have to be ballistic and learn to generate sequences, which in principle a language model could, sequences of lines on paper in order to replicate an image, but it actually sees the kind of stuff that it produces. And as a result of that, you can ask it to complete drawings that are started or to erase parts and to basically now have a playground for studying agentic behavior, right? It can do revisions to what it has done before. And all of this is happening in the context of a model that's exposed to an actual environment, which is in this case just the drawing environment.
Is it strictly self-supervised, or is there a supervision loop?
There's supervision, like in everything. So in this case, we were able to even embark on this because there are various data sets out there, like QuickDraw, for example, that have ground truth strokes associated with images. So people were drawing things, and then you can use those ground truth line strokes as a training signal to just say, okay, if I show you this image, generate this sequence of strokes. If I show you that image and I ask you to replicate it, then generate that. If I show you this partial image and I ask you to complete it, then again we have the ground truth to train the model. And so that was the starting point, so that we can fine tune the pre-trained language model on the ability to misuse the outputs it generates to talk about things that it does, like drawings. In that case, it's not an extra head; it's basically just using tokens. And then that is now the starting point to fine tune it with reinforcement learning, where the model can get asked to draw something that looks like a fish, and then it can make some attempts, maybe with high temperature, to do it. And then a classifier can say how good is what you just tried to do, how much does it resemble a fish, or whatever. And then that can be a learning signal that then allows us to fine tune that model with RL.
Interesting, interesting. We talked a little bit in the context of your transitory comment about, kind of where you think this is all going. Um, maybe that's a long term viewpoint. Well, I guess I can ask you, what's your viewpoint of the term or the cycle time here? Um, but I'm just curious, like, how you play out in time the evolution of AI reasoning.
In terms of predicting when what will happen, or more
Yeah,
like
what's
what
next?
will
What
happen.
what are the time frames? What's your
Yeah,
assessment of complexity? Like, I don't want to ask you to pull out a crystal ball, but also I do.
exactly. I know. I got a bloody nose there not too long ago when I was made a bet a few years ago that by I think 2021 or something, we're going to have an avatar video chat like you and I have right now,
Uh-huh.
where based upon what the person is saying with realistic rendering through GANs and whatever was the rage back then, maybe diffusion models now, whatever it is, uh, you wouldn't be able to tell whether you're talking to a person or an AI generated avatar. That hasn't happened yet. I
Uh-huh.
still think it's just 2 years out, but it has been 2 years out for a while. I think it's not completely unreasonable to assume that we're going to get to that point. Um, but we're not quite there yet. And other than that,
So take your the predictions to follow with an appropriate size grain of salt.
that's right. Yeah, predictions never really work though. um, as some people pointed out, Jeff Hinton amongst others, um, either we drastically underestimate or we drastically overestimate capabilities
Mhm.
for some reason. I don't know why that is, but it
Yeah.
seems to be a constant. Um, yeah, but I think there's a fairly obvious progression going on right now where language is getting significantly good. If we can get recurrence back, which is to be seen, but if we can get language, or keep language but get recurrence back, and combine in the best possible way the ability to process language with perceptual input and taking actions, so building proper agents. To phrase it very carefully, we're going to make significant progress in AI over the next few years.
And so one aspect of this is recurrence. You've spoken in length in this conversation about
Mhm.
that. Are there other missing building blocks that you think are needed?
Mhm. So yeah, recurrence goes hand in hand with memory. So that is missing in the same way. There is a total mystery when it comes to memory that may need to be solved, which is something that some people call fast weights,
Hmm.
where learning can happen at many different timescales. I can tell you a fact, like I was born in Germany, and then you're gonna keep that. And if I meet you in 3 weeks, you might still have that piece of information. Like, hey Sam, where was I born? And you're just gonna say in Germany somehow, right? So you can do fact learning instantaneously, just like that. And then there is another kind of learning, maybe another kind. We don't know what the relationship is, but there's another kind of learning, which is what we typically do also with neural nets, which is slow synaptic adaptation, being exposed to many examples of a task and then slowly adapting the weights in the network. So you get better at solving that task. And what is the relationship between these two, right? So uh, does that why can you in 3 weeks presumably still know that I was born in Germany, um, if not through some kind of synaptic adaptation? Or can you maybe? If not, then what has to happen for that synaptic adaptation to take its effect? Given that I just told you that thing, and you probably don't even think about this anymore for the next 20 days until I come back and ask you or something like that. So what's going on between these two, at least these 2 points on a maybe a spectrum or maybe qualitatively different types of learning or so. So that's still a bit of a mystery, and then maybe it has to be resolved. Maybe it without resolving that, some significant progress in AI is not going to happen. I don't know. Nobody really knows for sure. So, but that's memory, and it has to do with recurrence in some way.
Yeah.
I would assume recurrence in general has to do a lot with memory and so on. So that's clearly one missing piece. Then, other than that, I think there is a fairly straightforward linear path. It's going to require a lot of work, but there's a linear path in improving grounding seriously. So, not the industry term grounding that you know something about database entries and stuff, but really infusing the embeddings, or let's say brain states or feature vectors as you use language, with sensory information and information about yourself. And that goes very, very far. I think, and I think it's the key missing piece. So it goes as far as potentially having an agent have to develop a sense of the word I, which is also a beautiful and long-standing mystery in AI, which is how can the word I emerge for humans, and what exactly does it mean to an agent to say I, letter I, not the I.
Mhm.
So I have a sense of self. And so that may be fundamentally needed in order for the system to solve a variety of problems, because it needs to know that it did that action, it's on itself, how does it interact with other agent, and all of these kind of things. And it's a total mystery, a mystery dating at least back to Buddhist practices, the emergence of Buddhist practices several thousand years ago. And it's going to be really fascinating to see what we're going to learn about the, the emergence of the concept I, as we're trying to instill that in AI models going forward.
Mm, mm.
Okay, that's a bit
I feel
philosophical.
like you're opening the door to the second hour of our conversation, but I'm not going to take the bait. Although I really want to. We're gonna have to save that for
That's
our
right.
fourth
Look
interview.
forward to that.
Roland, it's been really wonderful to reconnect and to learn about some of the ways that you're exploring neural reasoning.
Thank you so much. It was great to be here again.